Hello, everyone. My name is Zixian Wang. You can call me Promoto. I'm a third-year PhD student in University of Sydney. And today I will talk about the reliable stellar abundances of individual stars with the Mills integral field spectral graph. And as we all know, the galactic archaeology is at present being prepared by a number of complicated or ongoing large-scale spectroscopic surveys like GALA, Apogee, and LAMOST. And this multi-object spectroscopic surveys combined with some data-driven PEM models make it possible for us to obtain precise stellar labels for millions of stars. However, one issue on all these surveys is that traditional multi-object fiber spectrograph cannot do dense fields, in particular the bulge and the clusters, because the fiber cannot be placed too close to each other on the sky, making the observations of clusters and the bulge very difficult. Therefore, we need a new instrument which can help to extract the stellar spectra from these fields. Finally, we found the Muse, which is traditionally used to study external galaxies, can be used to overcome this problem. So the Muse, or multi-unit spectroscopic explorer, is a second-generation integral field spectrograph that is installed for the VLT of ESO. And it has a wavelength region in optical and some in near infrared, with the field of view of 1 arc square and the spectral sampling of 0.2 arcsecond, with a resolution around 3000. Here's a brief plot showing the format of Muse data, which is called data cube. Basically, it is a 3D cube with two of them are already on deck, like an image, and with a third axis, which is wavelength. Briefly speaking, Muse contains spectra of any pixel with tiny size of 0.2 arcsecond square. So Muse offers a way to solve the issue, as we can get the spectrum for every pixel. Since the first light, most of the objects Muse focus on are galaxies, external galaxies, mainly helping scientists to research on the morphology, chemical information, kinematics. However, some research groups are using Muse to observe some dense fields with full of stars. See red image, which is an observation towards the galactic bulge. Most of them study the radial velocity, temperature, longitude, metallicity, and from the spectra in dense fields. For now, one idea comes to my mind. Since we have the spectra of stars in dense fields, we now have the opportunity to determine more chemical abundances. So in this study, by brief summary, what we achieved is we found a way to obtain stellar labels of temperature, longitude, metallicity, and also some chemical abundances from Muse observations on stars in dense fields. Now I will introduce the steps of extracting parameters from Muse observations. Firstly, we have an input catalog from other surveys, maybe Gaia-2, SkyMapper, and a Muse or data cubes that we want to extract the spectra from. So how do we get the spectra? Well, we use PyperMuse, which is a Python package specific to stellar spectral extraction from data cubes in crowded fields. Briefly speaking, it will first estimate the PSF for each star, and then fit the FWHM and the position profile as a function of wavelengths. Finally, sum all the flux together and combine different layers in wavelengths to build the spectra. So it is a super great algorithm to extract the spectra from data cubes. So back to this flowchart. Now we have Muse spectra with resolution of 3000. And here comes the new question. How do we derive the parameters? Well, there are several ways to do that. We can develop a model by ourselves, like setting a training set of Muse spectra with labels from GALA or Apogee. But this process will be complicated, and also there are not enough stars, common stars from Muse and the other surveys that are allowing us to do that. It seems like the road has come to an end, but actually it's not. Here I will introduce the flashpoint in our project, which shows how we can achieve this. We found that LAMOST and Muse have similar resolution and similar wavelength range. So if we can degrade the mu spectra to Lamont resolution and just treat it like Lamont spectra, we can directly use some neural network model to get the stellar labels. Since we have precise line spread function of both instruments, we can do this. Another good advantage is that when we degrade the spectra to a lower resolution, we can increase the signal to noise. Here's one example of the comparison of degraded mu spectra with Lamont of the same star. The gray regions are masked areas due to the telluric band, which will not be used when measuring the parameters. And from the residuals, we can see the degraded mu spectra is really similar to Lamont, with the difference about less than 2%. So now after degrading mu's to lower resolution, we can use some neural network model to build for Lamont spectra to measure the stellar labels. Now we will go straight to this part. Here I introduced one model by Monsheng. They developed a neural network model to derive about 20 stellar labels from about 8 million Lamont spectra with some constraints on the theoretical stellar model. It can precisely extract the parameters from Lamont spectra with uncertainties of temperature about 70 Kelvin, log G about 0.1 dex, and chemical abundances about 0.1 dex. To build the model, there are two training sets. One uses Lamont spectra with labels from Galan, and another uses the labels from Apogee. With the given stellar labels, it is a really important work which proves that we have the ability to estimate many stellar labels from low resolution spectra, or in other words, put low resolution spectra on higher resolution survey scale. Here's one example of the comparison of mu spectra with the best fit predicted by this model. From the residuals, we can see that DDPen is well behaved on mu spectra with the residuals less than about 1%. So now after degrading mu's to lower resolution and fit with the model, we can get the stellar parameters. And after doing some precision check, we can get, our final catalog. And now we want to check how the parameter from mu spectra behaves. So we find 84 common stars in Lamont and the mu's observation by now. After precision check and the signal to noise cutoff, there are 27 stars left. Now we want to see the difference of each label derived from mu spectra and the Lamont spectra by this model. In this figure, we plot the difference of labels from mu's and Lamont spectra as a function of metricity. The dots in the plot are those 70 stars. The left and the right column shows the result by running different models. The DDPen Galan model on the left side, and the DDPen Apogee model on the right hand side. We also calculate the mean and the standard deviation value for the differences shown in the corner of each subplot. From this figure, we can see the difference of labels from mu's and Lamont spectra are aligned to 0 point, which means their stellar labels are consistent. Now comes to the most exciting part in this study. Here we tested the performance of DDPen model on dense fields. As this plot shows, we selected 29 data cubes of from 9 fields towards the galactic center. Then we follow the steps in the flowchart and derive the stellar labels for all the stars in these fields. Next, we will select the 2 special regions and plot the magnesium versus metallicity distribution with comparison of previous studies to verify these performances. For the first field, we selected 92 stars in the galactic bulge with a distance to the galactic center less than 3.5 kpc. We also plotted the same figure from previous study as a comparison, which uses the Apogee data. We can see both plots have 2 similar sequences. One is the metal pole alpha-rich stars. The other is the metal-rich upper-pole stars. So even though we only have 92 stars with such a low resolution, compared with Rojas plot, which has more than 1,000 stars from Apogee, we can still show similar distribution of stars in the field. We also plot the distribution in the field of the inner disk with 3 to 5 kpc. The right panel in the previous study is from Freeman's hidden plot. You may see that in Sandeep stock. In this field, both plots are in agreement. again, we can see even with such a small sample size, we can still replot the similar trends with studies using the high resolution service. Therefore, we can conclude that DDPen can help us to study the chemical abundances of stars in dense regions. So I will leave the summary here, but I want to emphasize two aspects. The first one is, in this study, we can open a door for applications to data collected by other spectral graphs having a resolution similar to Lamo's. And also, this study provides a future opportunity to observe resolved stellar populations for other galaxies and measure their stellar abundances. And that's all my talk. Thanks for your listening. I will take the questions.
Great. Any questions? Yep.
I was just going to make the point that I think Pemortel was very humble about his achievement, because I think the future is going to be about observing star formation histories in dense fields, external galaxies on ELTs. And amazingly, I think it's going to be driven by integral field spectrographs, not by multi-object spectrographs like 2DF, because you just can't get fibers close enough. So integral field spectrographs, I think, I'm guessing, will be, with adaptive optic feed, will be a really profound way to probe star formation histories in Virgo, for example, or southern clusters, going much beyond the local group. So I think this is really the way forward.
Thank you, Jos.